Hello everyone and welcome to Calc Lesson number 11. Today we are going to finish up section 2.2 and we are going to be talking about rates of change. Already this chapter we have seen how the derivative is used to determine slope. The derivative can also be used to determine rate of change of one variable with respect to another. Applications involving rates of change occur in a wide variety of fields, including population growth rate, production rates, water flow rates, and then velocity and acceleration, which we're going to be working with today. So the function that gives the position relative to the origin of an object as a function of time t is called a position function, and we are going to be labeling that as our function s, or s of t. Then we can define our average velocity as the change in distance over the change in time, also noted as delta s over delta t, which is really just the slope of the secant line. So let's take a look at average velocity in terms of an example. A ball is dropped from a height of 100 feet. The ball's height s at time t is the position function, which is given to us here. S of t equals negative 16 t squared plus 100, where s is measured in feet and t is measured in seconds. Here we want to find our average velocity over the following intervals, starting with the interval from 1 to 2. Remember, average velocity is the change in position over the change in time. So we want to find the change or the difference in the position on the interval from 1 to 2, which we can do by evaluating our position when time equals 2, and then subtracting when we evaluate our position when time is 1, over, and then our difference in time would just be 2 minus 1, again just finding the slope of that secant line. Now we just need to evaluate at time equals 2 and time equals 1, so I'm going to quickly just go on this side here and think. S of 2 would be negative 16 times 2 squared plus 100, which I believe gives me 36. And S of 1 would be negative 16 times 1 squared plus 100, which I believe gives me 84. Plugging those back into our average velocity formula, we would have S of 2 is 36 minus S of 1 is 84 over 2 minus 1 gives us negative 48 over 1, which we can write as negative 48. So our average velocity on the interval from 1 to 2 would be negative 48 feet per second. We want to do the same thing on the interval from 1 to 1.5. So just like we did with our first interval, we want to investigate the change in position over the change in time, again by evaluating our position at 1.5 and again at 1 over 1.5 minus 1. Just like I did before, I'm going to come to the bottom just to evaluate S of 1.5. When I plug in 1.5 here, I get negative 16 times 1.5 squared plus 100. One 1.5 squared gives me 2.25. So then I have 2.25 times negative 16 gives me negative 36 plus 100. So S of 1.5 gives me 64. Now I already have S of 1 from my first problem, so I can now go back and plug into my average velocity equation. So I have S of 1.5 is 64 minus S of 1 is 84 over my change in time, so 1.5 minus 1. Doing this, 64 minus 84 gives me a negative 20, and 1.5 minus 1 gives me 0.5. So I have negative 20 over 0.5 simplifies to negative 20 times 2, which gives me negative 40. So my average velocity on this interval from 1 to 1.5, so that smaller time interval, is negative 40 feet per second. And finally, we want to do that very same process on an even smaller interval from t equals 1 to t equals 1.1. So we're looking at an even smaller interval of time. The process, though, is going to be the same. We are still looking for delta s over delta t, which means we're going to be looking at s of 1.1 minus s of 1 over that change in time, 1.1 minus 1. Again, I'm just going to jump to the bottom here to plug in for s of 1.1. I would get negative 16 times 1.1 squared plus 100. So this gives me negative 16 times 1.21 plus 100, which gives me negative 19.36 plus 100, which gives me positive 80.64. Whoops. Again, I already have s of 1 from my original problem, so now I can go back to my average rate of change formula and I can plug in. Plugging in for s of 1.1, I get 80.64 minus s of 1, which remember was 84, over 1.1 minus 1. 80.64 minus 84 is going to give me a negative 3.36. Over 1.1 minus 1 gives me 0.1 or 1/10. So then negative 3.36 keep change flip would be times 10. So this gives us negative 33.6. So we can say our average rate of change on that interval from 1 to 1.1 would be negative 33.6 feet per second. And we just want to take note that the average velocities in each of these intervals are negative, indicating that our object is moving downward. In the first example, we were looking at the average velocity over intervals that were getting smaller and smaller, but what if we wanted to look at the velocity not on an interval but at a specific instance? Just as we can approximate the slope of a tangent line by calculating the slope of a secant line, we can also approximate the velocity at time t by calculating the average velocity over a small interval. In general, if s of t is our position function for an object moving along a straight line, the instantaneous velocity of the object at time t is v of t, our velocity function, is the limit as delta t, the change in time is going towards 0, is getting really small, of s of t plus delta t minus s of t over delta t, which hopefully looks very familiar. It looks just like your difference quotient, which we learned is just the limit definition of the derivative. In other words, the velocity function is the derivative of the position function. Note, the speed of an object is just the absolute value of its velocity, since velocity has a positive or negative sign to show direction, and speed cannot be negative. In general, the position of a free-falling object, neglecting air resistance, under the influence of gravity can be represented by the equation s of t, our position equation, is equal to 1/2 g times t squared plus v sub 0 times t plus s sub 0, where s sub 0 is our initial height of the object, v sub 0 is the initial velocity of the object, and g is the acceleration due to gravity. On Earth, the value of g is approximately negative 32 feet per second or negative 9.8 meters per second, so we just want to pay attention to the units that we are given in each problem. So let's take a look at an example. At time t equals 0, a diver jumps from a platform diving board that is 32 feet above the water. Because the initial velocity of the diver is 16 feet per second, the position of the diver is given to us as s of t equals negative 16t squared plus 16t plus 32, where s is measured in feet and t is measured in seconds. So we're going to answer two questions here. The first thing we want to answer is, when does the diver hit the water? So we want to notice that we're looking at where the diver's position here, so we're going to be looking at our function s of t. Oops. And notice that the 32 feet, our initial position, was defined as being above the water. So if we want to know when we actually hit the water, we want to know when we are 0 feet above the water. So we want to take our position function and set it equal to 0. So we're going to take this negative 16t squared plus 16t plus 32 and set that equal to 0, and then solve for t to answer the question of when. Negative 16, 16, and 32 all have a greatest common factor of negative 16. I'm going to factor that out, so I'm left with t squared minus 1 minus 2 equals 0. Now that t squared minus 1 minus 2 I can actually factor, leaving my negative 16 on the outside. Factors of negative 2 that add up to negative 1 would be negative 2 and positive 1. Zero product property says I can take each factor and set it equal to 0. T minus 2 equals 0, t plus 1 equals 0. So I get t equals 2 and t equals negative 1. Remember that t stands for time in seconds. So because we cannot have a negative time, we would say that the diver hits the water at t equals 2, so at 2 seconds. The next question we want to answer here is, what is the diver's velocity at impact? So now we want to actually look at velocity. Notice we were only given information about position. So we have our s of t, our position function, but now we want to talk about our velocity. And then when we say at impact, we mean when he hits the water, at the instance the diver hits the water. So we mean at, from our earlier problem, t equals 2, because that's where we found he's going to hit the water. So we know our velocity, v of t, is equal to the derivative of our position function s prime of t. So let's look at our position function s of t. And then from there, we want to go ahead and take the derivative. So we can write our velocity, v of t, is equal to the derivative s prime of t, which is equal to, using our power rule and our constant multiple rule, negative 16 stays in front, but we bring the 2 down. That gives us negative 32. Our exponent goes down by 1, so we're left with t. Plus, we keep our 16, we bring that 1 in front, and then our exponent goes down to 0. So our velocity function, v of t, is equal to negative 32t plus 16. But remember, the question was actually the velocity at impact, so we want to look at the velocity when t equals 2. Plugging in, we get negative 32 times 2 plus 16, which gives us negative 48. And because this is velocity, we want to go back to our units and write this as feet per second. With this last part of section 2.2, homework 11 is short, just numbers 93, 95, 97, and 99. You can reach out to your teacher if you have any additional questions.